Hello, I'm going to talk today about simple circuits. So we'll start off by drawing a cell, representation of a cell, and I'll make that a little bit lower down, I think. It's going to be, I'm going to represent it's a 12 volt cell. 12 volts is an unusual number of a cell. Most cells come is 1.5 and then multiply them up to get batteries, so 3, 4.5, 6, etc. But 12 volts makes a nice number for calculations and explanations. So the simplest type of circuit you can have, let's say, a very simple circuit, have resistor in a circuit like that. And conventional current goes from positive to negative, so the current would flow in this direction. Now, in reality, it doesn't in fact flow from negative to positive, but for when we're talking about circuits and many ideas with electricity and magnetism, historically we're assuming, and in practice we still use it, flows from positive and negative. And let's say this resistor has a resistance of, say, 4 ohms. Okay. The first thing we're going to do is a very simple but very useful equation, is this equation here, often known as Ohm's law equations. V equals I times R. Okay. So, if we wanted to calculate the current flowing through that circuit, we would simply arrange that to be current is equal to voltage divided by resistance, which is equal to 12 over 4, which is equal to 3 amps. So there you go, the three things about the circuit. You've got 12 volts supply, 4 ohm resistance, and 3 amps going through it. Now if you were to get a voltmeter and put it across here, the voltmeter always goes, if you like, across the component or parallel to the component. If we put a voltmeter across there, we would expect that to read 12 volts. And if we are to put an ammeter into here, so ammeters always go in series like that in the loop as the current flows through it, we'd expect an ammeter there to read 3 amps. Now we are assuming that there is no internal resistance in the cell, and for a lot of the stuff we'll be doing, we'll be assuming there will be no internal resistance, but we can talk about that later. Okay, so let's move on. Now I'm going to draw now exactly the same circuit. So there you go. So our cell, 12 volts. 12 volts is the supply, sometimes known as the EMF. Traditionally it stands for the electromotive force, but it is not a force, but it has stuck. So 12 volts from the cell through our resistor, and I believe I said it was a 4 ohm resistor. Now, another way for this is 12 volts is to talk about it as a potential difference of 12 volts. So, therefore, we'll talk about potential difference, is a bit difference in potential. So, how we can think about this is that the positive, which is a long one, we can say here it will have a potential of 12 volts, and then at the negative end here it will have a potential of 0 volts. So as it goes around the circuit, the potential must drop from 12 down to 0. Now, in these circuits we draw, almost always, we'll assume that the wires, the connectors here, have no resistance at all. And potential will only drop across the resistance. So if we got 12 volts here, if I took a point here, that will also have the potential of 12 volts. But now we got a resistance, and this is the only resistance in this circuit, and we've got 0 volts there. Therefore, we'll therefore have a potential of here of 0 volts. So you see, all the potential here is dropped across this resistor. So if we put our voltmeter in here, V, the voltmeter V would equal 12 volts, and that is the potential drop across this circuit. Okay, now if we were to draw another circuit slightly more sophisticated, so I'll start again with this very useful number 12 volts, and in here I will put not one, I will put 2 resistors. Okay, now this time we're going to make them both identical resistors, so we'll have this one as 4 ohms and this one also as 4 ohms. So again, we'll think about this idea of potential drop. So we start here, we've got 12 volts this side. Now the time the potential drops all the way back to here, we've got to go back to 0 volts here. Okay, so we get a potential difference across there as 12 volts, potential drop across it as 12 volts. So we start here 12 volts, no resistance, no resistance. So we get here, we got 12 volts. We're going to have a series of resistors, no resistors there, so therefore we're going to have 0 volts here. Now because those 2 resistors are identical, we're going to have equal potential drops. So therefore we'd have in the middle here, we'd have a potential of 6 volts. So therefore the potential drop across that resistor will be, let me draw it like this, like that. Here will be 6 volts, and the potential drop across this resistor here will also be 6 volts. So therefore it'll drop from 12 all the way back down to 0 here, which will stay the same back to there. Okay. Now another way of looking at this is to look at it through the very useful equation V equals IR again, and we can get exactly the same result if we apply the idea of V equals IR to it. So if I rub this off, and draw it again, and here's the resistors, what we'll do is we will attempt to calculate what the potential drop is across there using this V equals I R formula. So we have our 12 volts there. So, and let's assume again this is the direction of the current. Now the first thing we're going to calculate the current. Now the resistance here is going to have to be the total resistance, and as there's no branches off here and these are in series, the total resistance, our total, is equal to 4 ohms plus 4 ohms. When resistors are in parallel it doesn't work like this, but these are in series because they're in line in the direction of a single flow of current. So that of course equals 8 ohms. Now our total potential drop across here is going to be 12 volts, because we're going to have our 12 volt potential there and 0 volts here, because that's no resistance there, no resistance there. So we're going to find that the current I is equal to V over R, which is equal to 12 over 8, which equals 1.5 amps. So we've established now that the current is 1.5 amps, so we can write 1.5 amps there and 1.5 amps there. Okay, so, but we still haven't calculated what the voltage is across each of those resistors. And to do that, again we apply V equals IR. So, as I'm running out of space, I will rub this out, draw it again, but this time we know what the current is. So here's our 12 volts EMF, here are two resistors of 4 ohms each, and comes back there. Okay, so we now know from previously we calculated that the current is 1.5 amps. So in current terms, what goes out must come back in again, like that. So if we just take one of these resistors, okay, and let's calculate what the voltage must be just across here. So imagine we put a voltmeter in here and call this one V1. So apply V equals IR again. So V equals IR. Now in this particular case, we know that the current, which doesn't change in a simple series loop like that without branches off, we're going to find that the current is just 1.5 amps. So V equals 1.5 multiplied by the resistance there times 4. So 1.5 times 4 is in fact 6 volts. So V1 is 6 volts. Those two are exactly the same, so V2 equals 6 volts. So we have a potential drop across here of 6 volts and a potential drop across here of 6 volts, which makes sense because we have to drop from 12 volts over here across to 0 volts over here. Okay, I'll stop right there and we'll talk more a bit later.